Hey everyone, I'm McKay Levingood, and today we are going to talk about the motion of a falling object. We're going to get started with an introduction. The purpose of this lab is to observe the motion of an object that is dropped from rest and falls somewhat slowly straight down. We're going to compare the computational model observations to the experimental observations using physics principles. Some of the physics principles and key terms that we're going to use include Newton's second law, which states that the net force is equivalent to the mass times the acceleration. Aerodynamic drag force, which is the force on an object that resists its motion through the air, and the gravitational force, which is the force exerted on an object close to the Earth's surface. The drag force and the gravitational force are in opposing directions. This lab, we're going to get data from two different methods, the experimental method and the computational method, and then we're going to compare the data. So in the experimental method, a ball will be dropped from height h and it will fall to the ground. The movement of the ball will be analyzed using tracker. And the system in this scenario is the ball, and the surroundings include everything else around the system, which in this scenario would be the gravitational force and the drag force. For the computational method, GlowScript coding will be used to create the model. During this lab, we are going to have to calculate a few things, and these are the formulas we're going to need to use. First, we have the velocity update formula and the position update formula. Then in the left corner, we have the force of gravity. And then to the right of that, we have the force of gravity close to the Earth's surface. In this scenario, we are close to the Earth's surface, so we will be using F equals mg. Then we have the net force and the drag force. Now we are going to look closer at the experimental method. As you can see from the video, a ball was dropped, and using tracker, we analyzed the motion of the ball. This is how we got the graph and then the table that goes along with it. As you can see, the velocity increases over time due to the gravitational force, which causes the ball to accelerate downward. Computational method, first we did this with no drag force. So in line 37, we have the input of the ball's mass, and then in 40 and 41, we're plugging in the initial conditions. We're setting the drag force equal to 0 because in this computation, we're neglecting it completely. And then in line 71, we're plugging in the F net values. In this scenario, the net force on the ball is equivalent to the gravitational force because that is the only force causing the ball to accelerate. And then we have the velocity update formula and the position update formula later on in the code. Using that code, we got this velocity versus time graph and the position versus time graph. As you can see, the velocity increases. It's in the negative direction, so it's a downward slope, but it is increasing in magnitude over time. Now we're going to slightly change the code to accommodate for the drag force. So this is still the computational method. This time we are just inputting a value for the drag force. So we put in that B value, and then in line 71, we have the formula for gravitational force. And then in line 72, we have the formula for the drag force. In this scenario, there are two different forces acting on the ball. So we have to add the two forces to acquire the net force, which is shown in line 73. And then later on in the code, as before, we have the velocity update formula and the position update formula. In this computational method, we included the drag force, and we acquired this position versus time graph and this velocity versus time graph. As you can see, the velocity versus time graph is curved slightly, meaning that the drag force altered the motion of the ball. The ball is no longer accelerating downward at 9.8 meters per second squared. It's now slightly less because of the drag force in the opposing direction. Here we have a comparison of the three methods that we use. We have the experimental, computational without drag, and then computational with drag. As you can see, the graphs have a fairly similar shape and curve to them. They're slightly different due to the air resistance in the real life experiment. As we were discussing earlier, The velocity is different between the no drag versus drag computational method. This means that the velocity of the ball when drag is included is nonlinear, and it affects the terminal velocity. The terminal velocity is when the drag force is equivalent to the force of gravity. And that's it for today's lab. Thank you so much.